Very good. That is really dog and bugs. Genius.
G'day again, Year 11. Welcome back to your next lesson on mathematics. Today we're starting off with a flashback from the last video on probability trees. The question is, there are 15 girls and 7 boys in a class. We are going to choose 2 students at random to be class representatives. So we want to find what is the probability that we choose 2 students of the same gender. We've got a probability tree that's been started off, and we're going to finish off and then answer the question. So this is a standard maths HSC question from 2013. Hit pause and have a go yourself before I spoil it for you. Okay, so completing the rest of the probability tree is going to look like this. So we've got 15 out of 22 girls and then 7 out of 22 boys. And because we can't pick the same person twice, this is a non-replacement question. So if we've picked a girl on the first one, there's now a 14 out of 21 chance of picking a girl on the second try, etc. Okay, so we're trying to find the probability of getting 2 students of the same gender. So there's 2 ways we can do that. We could go a girl and a girl being selected, or we could be choosing a boy and a boy. As we saw last lesson, if you want to get down the branch of a probability tree, you're going to be multiplying, because we're saying and then if there are multiple branches that fit the criteria of the question, we're going to plus both of those answers together. So we're doing boy, boy, or girl, girl. So we do boy times boy plus girl times girl. Simplify your answer, and it works out to be 6 out of 11. So awesome work if you got that all by yourself. Okay, today's lesson is the last part of the probability topic for Year 11 Advanced. It's called conditional probability. This is something that you would not have seen at all in Year 9 or 10. So yeah, this might be a bit of a tough one. I definitely think this is the most complicated part of the topic. So yeah, take your time. If you're not getting it at first, that's all right. That's pretty normal. And of course, send me an email if you have any questions at all. All right, let's talk about Monopoly first and foremost. Very important game. I used to play a lot of Monopoly when I was a kid because I'm a loser, I guess. And I used to always be wondering, obviously you're trying to get these properties to try and make some money and bankrupt your friends and family. That's a true life story. And I was always asking myself, I wonder what is the most profitable set of properties mathematically. And so to answer that question, you've got to analyze the tools that you're playing with, which is the double dice roll. Okay, so here are the outcomes when you roll 2 dice and you add together the outcomes, like you were rolling for a move in Monopoly. The lowest roll is a 2. You can only do that one way, which is a 1 and a 1. Highest roll is double 6. Now, as you can see here, the most common outcome from a double dice roll is a 7, because you can get that 6 ways out of a total of 36 chances. So the most common outcome when you roll 2 dice and sum the result is 7, followed by 6 and 8. Okay. Now looking at this probability board, you're asking yourself, what is the one square where at some point you are more than likely going to end up? And if you're familiar with the game of Monopoly, you'll know the answer is at some point you're going to be in jail, right down here. Okay? Once you've been in jail, you are going to leave jail, and then you are going to roll the dice. And what are you most likely to get on your first dice roll? Probably a 7, maybe a 6, or maybe an 8 is most likely. So starting here, your first dice roll is more than likely going to land you smack bang here in Orange Town. So this is my mathematics advice for you today. If you are playing Monopoly with your parents maybe this weekend, or your family, because you have to stay inside and do nothing else, if you do anything you can to get the orange properties, you will win, because people always land on it because they land in jail. All right. There you go. Life hacks from maths. You're welcome. Let's do some maths. So let's talk about conditional probability. So let's kick off with 2 dice being rolled like we're playing Monopoly. We're asking, what is the probability we are going to see a total of 10 on the dice? Okay, a total of 10. Let's look at that grid of dice rolls again. We can see out of our 36 options, getting a 10 total is 1, 2, 3 options. So we can get 6 and 4, 5 and 5, or 4 and 6. So the probability of rolling a 10 is going to be 3 out of 36, which we can simplify to 1 out of 12. Okay. What about if we were asking, what would the probability be of rolling a 10 given that the first die is a 5? All right, so think about this. You're rolling 2 dice. You've already rolled 1 and you've got a 5, and now you're asking yourself, what's the probability I'm going to get a 10? Well, if you've already rolled a 5, to get a 10, you need to get another 5. And on the second dice, getting a 5 is a 1 in 6 chance. Okay, that's called a conditional probability. It's kind of like a probability of a multi-stage event where you already know the outcome of one of the stages. Okay, this is the probability of 5, given that we already have a 5. Okay, it's a 1 in 6 chance. So that's one you could do in your head with no real mathematics necessary. Let's look at one where you're gonna have to actually do some maths. So a tougher question. What is the probability of 2 dice showing a total of 10, given that the first dice shows an even number? All right, so you don't know exactly what's on the first die, but you know it's a 2 or a 4 or a 6. So this is an example of where we could, if we wanted to, use what's called the conditional probability formula that looks like this. All right, this is brand new for you guys. The way this is meant to be read is this is the probability of event A happening, given that event B has already happened. Okay, so it's read as probability of A given B. The way we calculate this is we find the probability of A and B both occurring, and we divide that by the probability of B occurring. I'll show you in a second why this formula works, but for now we're just going to use it and see if it works. Let's have a go. Why not? So there is a formula. It is on your formula sheet, but we're going to be using it in pretty much every question today. So we're looking for the probability of getting a total of 10, given that the first die is going to show an even number. So using this formula, we're going to find the probability of there being a total of 10 and the first die is an even number. So we're going to think about, out of those 36 trials that we saw from our grid, how many of them have 10 as a total and the first die rolled is even. We're going to divide that by the probability of the first die that we rolled being an even number, which is just going to be a half chance because it's just a dice, yeah? All right, so looking at our grid, let's just say that the top die is going to be the first one and the side one is going to be the second one. So out of our 3 chances of getting a 10, so our 3 out of 36 chances, how many of them also have the first die being an even number? Well, it could be this one because the first one's a 4, or it could be this one because the first one is a 6. Okay, this one here where the first one is a 5, that doesn't work. So for the top of the fraction, probability of 10 total and the first die even is this number and this number, so it's 2 out of 36. Like we said, the probability that the first die is even is going to be a 3 out of 6 chance, which we'll just write as 1 out of 2. We're going to slightly simplify, not fully simplify, this fraction to 2 out of 18, and there is our probability. Which kind of makes sense, because if he told me that the first die was even, it means that we're not looking at all 36 outcomes. We're just looking at these 3 sets of 6, so these 18 outcomes where the first die is even. Out of these 3 sets of 6, so out of these 18, how many of them have a 10 in total? That one there and that one there. So it's 2 out of 18. So the formula works. Hooray! All right, so let's have a look at why this formula works, or how this formula works. So the probability of A, given that B happens. So let's think in terms of Venn diagrams. Normally, the probability of A is kind of like how many things in A out of how many things in the total sample space. So it's A out of total. Now we're kind of asking, what's the probability that you're in circle A, given that you're already in circle B? So now your bottom of your fraction isn't the entire sample space. The bottom of your fraction is just B. You already know you're in B, that's your total. If you're already in B, what's the probability that you're in A? Well, you've got to be in the overlap. So the top is the overlap, the bottom is the total of B. That's why the formula works, if that kind of makes sense. This second method makes more sense to me personally. So the way I think about it is, if you've got A and B being independent events, which we looked at last lesson or the other day, independent events do not affect one another's probability. Okay, so if you want to find the probability of A and B occurring, it's the probability of A times the probability of B. Easy peasy. Now, if your events are dependent, which means that the outcome of one does affect the probability of the other, you get this setup. We have the probability of A and B occurring, is equal to the probability of A, that happens, and then we multiply by the probability of B, given that A has just happened. All right, so in the first case, the probability of B didn't change because they were independent. In the second sense, the probability of B changed because A happened because they were dependent events. All right, that's the difference. This second line here, if we rearrange it, we get this formula just here. All right, so this formula is just this second line rearranged. And that's what makes sense to me. But anyway, let's have some more practice of using this formula because they can ask some pretty scary sounding questions that if you use this formula, this one in green, they're actually not super scary. But let's have a look. Okay, here's our first example. We've got a card being selected from your standard 52 deck of playing cards. Find the probability that the card selected is a queen, given that the card is a picture card. Okay, so we're drawing out a card and I'm telling you, hey, this card is a picture card. What is the probability it is a queen? And if you're really familiar with your cards, you may already know your answer. But we're going to have practice using the conditional probability formula for these two simple questions, and then it'll be hopefully easier to apply it to the more complicated questions later on in the lesson. So we're trying to find the probability of queen, given that the card is a picture card. So we've got to find the probability of a card being both queen and a picture card, which, I mean, it doesn't really make sense because all queens are picture cards, but anyway. And then we're going to divide that by the probability of the card being a picture card. So let's think, out of your standard 52 card deck, how many of those are queen picture cards? Well, there's a queen in every suit and there's 4 suits, so it must be 4 out of 52 because all queens are picture cards. Now on the bottom, probability of a picture card. Picture card refers to jack, queen, or king. So there's 3 in each suit, 4 suits, so we've got 12 in total, so 12 out of 52. So there are our probabilities, 4 queens out of 52 and 12 picture cards out of 52. If we multiply the top and bottom of that fraction by 52, we just get 4 out of 12. So we've got a 1 in 3 chance, which again makes sense because there's only 3 types of picture cards. If you drew out a card and said, hey, this card is a picture card, what's the probability it's a queen? Well, you got a 1 in 3 chance. It's jack, queen, or king. All right, for the next one, the probability that we get a queen, given that the card selected is red. So we're going to find the probability of queen given red. So we'll find the probability of it being a red queen, and then we'll divide by the probability of it being red. So think about in your deck of 52 cards, how many of them are red queens? Well, there's 2 red and 2 black. So we've got 2 out of 52. Now half of our deck is red, so the probability of a red card is 26 out of 52. Again, we'll multiply top and bottom of the fraction by 52, and we get 2 out of 26, which is a 1 in 13 chance. All right, so if you've got a red card, the chances that it's a queen is a 1 in 13 chance. Again, if you know your cards, that's pretty obvious, but this is just a warm-up example. Okay, next question. We've got 4 identical spheres, numbered 1, 2, 3, and 4, put into a box. We're going to draw one randomly from the box. We are not going to return it, and then we're going to draw a second box. So on the first draw, we'll have 4 options, and then on the second draw, we'll have 3 options. So for our total multi-stage event, we'll have 4 branches and then 3 branches. So we'll have 12 outcomes in total. That's important, okay? 12 outcomes. Question A, what is the probability that the first ball drawn is numbered 4 and then the second one is a 1? Okay, so on the first draw, the probability that we get the 4 is a 1 in 4 chance. And then on the second draw, the probability we get the 1 is going to be a 1 in 3 chance. We want to find the probability of doing both. So as we've done many times now, we are going to multiply them. So a quarter times a third is 1 out of 12. Like I said, 12 possibilities in total, and one of those 12 is going to be a 4 and then a 1. Okay? Next question, a bit trickier. What is the probability that the sum of the numbers on the 2 balls is 5? So the last way we did it, 4 and 1, that could work. We could also do 1 and 4. We could also be doing 2 and 3, or we could do 3 and 2. So we've got 4 ways of getting a sum of 5. Now, a 4 and then a 1, that was a 1 in 12 chance. That's going to be the same for all 4 of these, okay? They're all equally likely. We've already calculated the probability of a 4 and then a 1. It was 1/12. So we've got a 1 in 12 chance of this, a 1 in 12 chance of this, so on and so forth. So if we add them together, we've got 4 lots of a 1 in 12 chance, which means it's going to be a 4 in 12 chance, which is going to be a third. All right, so these 4 outcomes are all going to meet the criteria, so we add them all together. Hopefully that is somewhat clear. Okay, and question C, given that the sum of the numbers on the 2 balls is 5, so given that one of these 4 things has just happened, what is the probability of the second ball is numbered a 1? So again, we could answer this really simply just by going on basic logic. So we've got a sum of 5. So like I said, it's going to be one of these 4 outcomes. What's the probability that's numbered 1? Well, it's only 1 out of the 4. So I would be expecting our answer to be 1 in 4. But we can double check that with our handy conditional probability formula. So we want the probability of the second ball being a 1, given that the sum of the balls is numbers is 5. So we'll find the probability that we get a 1 on the second one and a sum of 5. We'll divide that by the probability of getting a sum of 5. All right, so probability of having a sum of 5 and the second ball being a 1, that's this guy right here. That was our 1 in 12 probability. Okay, a 4 and a 1. 1 in 12 for that, and then the probability that we get a sum of 5, we just calculated that in part B. The probability of having a sum of 5 we got was 1 in 3. Okay, or you could write that as 4 out of 12. This way it makes it a bit more clear that we're going to cancel the 12s off top and bottom by multiplying. We get our answer of a quarter. Like I said, there's 4 ways we can do it. Having the 1 as the second ball is 1 out of the 4 options. Okay, so there's your answer, 1 quarter. All right, let's try another one. We've got on days with pleasant weather, the probability that Brent will walk his dog, Arnie, is 3/4. If the weather is unpleasant, the probability is now only a 1/3 chance of the dog being taken for a walk. Okay, question A. In a particular week, the weather was pleasant on Monday and then unpleasant on Tuesday. Find the probability that Brent walked Arnie on at least one of these mornings. Now, you have to be really careful when you have a question that's asking you for at least something, okay? Because at least one of these mornings, it means we could have walked him on Monday and then not on Tuesday. We could have done vice versa, not walked on Monday, but then walked on Tuesday. Or we could have walked on both days. Okay, so there's actually 3 things happening here that we would need to calculate and then add together. Or if you remember the question that we did the other day, there is actually a shortcut to this question. If we're trying to find the probability of walking Arnie on at least one day, what we can do is we can find the probability that Arnie doesn't get walked either day, and we can take that away from 100%. All right, so we're going to be really clever, and instead of working forwards and calculating 3 things, we're going to work backwards and only calculate 1 thing to save a bit of time. So we'll find the probability of not walking the first day and then not walking the second day. Okay, so on the first day we have a 3 in 4 chance of going for a walk, which means there's a 1 in 4 chance we don't go for a walk. Second day is a 1 in 3 chance of going, so a 2 in 3 chance of not going. All right, multiply these together and we get 1 in 6. So there is a 1 in 6 chance that we don't go for a walk on either of the days. That must mean, just by leftovers, that there is a 5 in 6 chance that we're going for a walk on at least one of the days, okay? Because it's everything other than not on both days, okay? 1 in 6 chance that we don't either means a 5 in 6 chance that we do either of them, okay? All right, bit of extra information. We have in the month of April, the probability of pleasant weather on any given day is 5 out of 8. Find the probability that on a particular morning in April, Brent walked Arnie. Okay, so we have to take 2 things into account here. First of all, the probability of good weather versus bad weather and what the effect that has on the probability of us taking the dog for a walk. So we're going to find out, first of all, the probability that it was nice weather and then we went for a walk. Or the other option is it could have been bad weather, but then there's obviously still a chance that we go for a walk in bad weather. So it is a multi-stage event. If you want to draw a tree diagram, it will help you keep track of it, but I'm just going to kick on with that one because I'm a mad rebel. So here we go. So 2 options. We can have pleasant weather and go for a walk, or it could be unpleasant weather and we go for a walk. To do both of these, we're going to multiply, and then to have both options, we're going to add them together. So we're going to go pleasant times walk plus unpleasant times walk. So we've got a 5 in 8 chance of pleasant weather, which means we've then got a 3 in 4 chance of going for a walk. So this is pleasant weather and going for a walk. Or if there's a 5 in 8 chance of pleasant weather, there's a 3 in 8 chance of unpleasant weather, which then gives us a 1 in 3 chance of going for a walk. All right, so pleasant and walking, or unpleasant and walking. That gets us a total answer of 19 out of 32. All right, now that's going to be useful for part C, which is the more challenging part. Find the probability that on an April morning, the weather was pleasant, given that Brent was taking Arnie for a walk. All right, so whenever we see the words given that should give us a hint that we should be using the conditional probability formula, this guy here. So we're going to be using probability of pleasant weather, given that the dog is being walked. And the formula says we've got to find the probability of it being pleasant weather and going for a walk, and then divided by the probability of the dog being taken for a walk. And the bottom of the fraction, we just figured it out in part B. So we've already done half the work. We've just got to recognize A, that we're using this formula. We've got to use it correctly, and we've got to find the probability of pleasant weather and going for a walk. All right, which is a part that we've already calculated just up here. This is pleasant weather and going for a walk. 5/8 times 3/4. That's the top of the fraction. Bottom of the fraction is the probability that the dog gets walked, which we calculated to be 19 out of 32. You can chuck that through your calculator and you get a final answer of 15 out of 19. So there you go. So for these more complicated conditional probability questions, there will be parts that help you sort of build this formula, because just getting part C up front would have been a really, really tough question because you've got to build all this by yourself, and that's pretty tough. So yeah, like I said, go slow. If you're not getting this at first, that's all right. Watch it again if you need to, or do some more practice questions, out of your textbook. Okay, we're going to do another because when I was learning this for the first time, I found that I needed to do a lot of examples before it really started to click. So I've put plenty of examples in this video. So I apologize if it's a long one, but let's just kick on. We've got the manager of the St. George Dragons notices that the team has a probability of 0.6, which is 60%, of winning if it is raining. However, they only have a 0.25 chance of winning in dry weather. Find the probability, the probability that it will rain is 0.3, okay? Question A, find the probability that the Dragons will not win. So we've got to do two things here. Okay, once again, if you are drawing yourself a tree diagram, I would recommend it, and it will make this question a bit more clear. I'm actually going to do that on the next one, but I couldn't be bothered for this one, so let's just kick on. Probability the Dragons will not win. Well, there's two ways they can do that. They could lose in good weather, or they could lose in wet weather. So we have to account for both of those options, and then we have to, as always, plus them both together because they both meet the criteria of the question. So we're going to find the probability of it raining and then them losing, or it could be dry and then they lose, which means we've got to multiply these, and then add them together. So hopefully you're getting the hang of this. We've done it many, many, many times now. All right, so probability of rain is 0.3, and then they have a 0.6 chance of winning when it's raining, which means they've got a 0.4 chance of losing when it's raining. All right, so rain times lose. We're plussing to that the probability that it's dry, which is going to be 0.7. When it's dry, they've got a 0.25 chance of winning, so they've got a 0.75 chance of losing. All right, so raining and losing, or or dry and losing. There are two possibilities. We get a total probability of 0.645, which is 64.5%. Okay, now for part B. Given that the team has won a game, what is the probability that it rained on that day? So if they won, working backwards, what's the chances that that it was raining? So we have a condition here, which means we need to be using our conditional probability formula for the 10th time today. So we are finding the probability that it's raining, given that the team has won. So our formula says we've got to find the probability that it's raining and they won. We're going to divide that by the chance of by the chance of win, which we can get from our previous answer because we found the probability that they do not win. All right, so for the top, probability of rain, like we said, is 0.3. When it's raining, the chances that they win are 0.6. So we're going to do 0.3 multiplied by 0.6. In part A, we calculated that there is a 0.645 chance that they lose, which means conversely, the leftover from 100, which is 0.355, that must be the chances that they win. All right, chances of losing, chances of winning. There's our formula. This fraction simplifies to be roughly about a half chance, about 0.50 from my calculations. And so there is your answer. So probability of rain and wind divided by probability of wind gets you about a half chance. So if it's raining, there's a half chance that they just won the game. Cool, fun maths. All right, to finish off, we're just going to do an optional challenge question. This is kind of like the questions that we just did. It's just not scaffolded, so you've got to do a lot of work by yourself. Let's quickly run through it. The probability that I cry during a maths exam is 80%. When I'm not in a maths exam, there's only an 8% chance that I'm crying. If I have a maths exam 3% of the time, find the probability that I'm doing a maths exam given that I'm currently crying. So this is some real life maths that you can take into your exam room with you. So we have a condition. So we need to find a conditional probability. Like I've been saying, these really complicated questions, if you're getting lost, you can sort of help yourself by drawing a quick tree diagram. So we've got maths exam, and then with a hat on means not maths exam. So we're doing a maths exam 3% of the time, so we're not doing a maths exam 97% of the time. Now we have crying and not crying as our second stage for the event. So we've got when I'm in a maths exam, there's an 80% chance I'm crying, which means in a maths exam, there's a 20% chance I'm not crying. All right, where are we getting the 0? All right, so there's an 8% chance I'm not crying when I'm not in a maths exam. So we've got not maths exam, crying is 8%, which means there's a 92% chance that I'm not crying. So there's all the facts and figures interpreted from the question, put into a tree diagram to make it a bit easier for us to follow, okay? Now we can use our formula. So we're going to find the probability of doing a maths exam given that I'm crying, which means we've got to find the probability of doing a maths exam and crying at the same time, which is going to be this top branch. We're going to divide that by the probability that I'm crying. And because there's two ways I could be crying, either this branch or this branch, we've got to account for both of them. All right, so the top of the fraction is going to be this branch, which is going to be 0.03 multiplied by 0.8. The bottom of the fraction, probability of crying, is this branch and this second branch where they both end in tears. Okay, so we're going to have 0.03 times 0.8 again. We're also going to have 0.97 multiplied by 0.08 and then plus together because it could be this branch or it could be this branch. All right, there's our calculation using our formula. We get a final answer of about 23.622% chance. So there you go. If I'm crying, there's about a quarter chance that I'm doing a maths exam based on the data in the question. All right, sweet. So you guys now need to rip into a few practice questions out of 707. I want you to pick at least 8 and see how you go following the formula, trying some by yourself. And as always, flick me an email if you have any questions. And I'll see you guys in the next video. Thank you so much if you made it this far. I'll catch you later. Bye.